Alright, so if you look at the section 1 example, I'm showing a couple of different things. So yeah, obviously there's a 500-pound concentrated load in the middle, and I'm showing this as a single line, but imagine a beam, right? You guys all know what the beam is. Just like imagine like a stick of wood or something that's supported at two ends, two columns. But so what you see here, imagine sort of like maybe like a bridging kind of condition. So these notations, one on the left side I'm showing a triangle, on the right side I'm showing the circle. That's kind of a conventional way of showing different type of supports. I forgot to paste the link for explanation for support types, but that's pretty much all you need to know for these two. So one is called pin joint, the other one's called roller joint. The only difference between these two, I mean, this actually almost doesn't matter for these problems because we are only looking at vertical forces, right? I'm not really applying any kind of horizontal or diagonal forces, but this is kind of a typical way of showing the support conditions. So on the left side, what's triangle, that one's called pin joint. What it does is, let's say it basically, so this is two-dimensional problem, right? So there's only x and y in this world that I'm showing on this screen. So what a pin joint does is it resists the force in x direction as well as y direction. In other words, if I try to, so the beam is supported on one end with this joint. What this resists is if I try to move it this way, it prohibits you from doing that, and also it prohibits you from moving it vertically. So basically, this triangular thing, which is called a pin joint, it can resist a force this way and that way. So it doesn't move either this way or that way, right? So, and vice versa, if you try to pull it off, it's not going to pull it off. If you try to pull it this way, it's not going to move. So basically, this is not moving, right? So it's resisting, in this two-dimensional world, it's resisting all direction of forces. On the other side, where you have this circular one, this is called roller joint, and pretty much exactly what it's called. What it does is it does not resist any type of horizontal force. So if I want to move this beam on top of this roller joint, it can freely move in this x direction. It's like a roller. But what it resists is if I try to crush this vertically in y direction, it resists that force. So it only has this vertical resistance in y direction. What's kind of counterintuitive is also it's supposed to be able to provide a resistance in other direction, which is if I try to pull this up, it prohibits you from pulling up too. So it's like it refuses to move this way or that way, but it's completely free to move along this way. So I hope that makes sense. Yeah? Okay. So for these beam problems, we won't really have to get into the details of like what they mean, but it's just a conventional way of showing a two support on two ends of structural system. Because if you think about it, if you think of a bridge or something, or any kind of these support condition, if both of them are completely fixed, sometimes what happens is like these two ends kind of move, right? So once the other end moves, this thing is constantly bent or something like that. But anyway, so this is just know that this is a conventional way of showing it, and when you see the triangle and round symbols, you should be able to understand what they are. Anyway, so we've already covered a slightly more complex version of this, so I'll go through this really quickly. But so for this, it's actually no-brainer because it's right in the middle. Like before we even do anything, I kind of know it's 250 and 250 on both sides. Oh, and not to forget that I'm using this force scale, which is 1 inch equal 10 pounds. So that's why this arrow that's 50 inch long is representing 500 pound force. Anyway, so because I'm applying this vertical load, I am to assume there's gotta be some sort of a vertical reactions on one end, on both ends. And so this is pretty much exactly what the beam is showing, but now I'm isolating just all of these forces and this line, and so this is called loading diagram. And so 500 in the middle, reactions on the side, which presumably we don't know yet. So then same process of labeling these zones between the forces. So first I would label this zone between R1 and 500, which is A. Next point is B, 500 on R2, and then between R2 and R1 below this beam thing, I'm gonna call this C, right? So then I guess last time I put the point on the right side, which is fine, but this time I'm just putting the point on the left side. It actually, for the beam problems, so before explaining what it is, so this is called, I mean, I guess I sort of explained last week, but this is called moment diagram. To draw a moment diagram that is sort of conventional style, it's actually easier if you put the point P on the left side. But really it doesn't matter that much, but if you want to draw a nice clean moment diagram, you might want to put the point P on the left side. But still, even if you put it on the right side, you can solve the problems without any trouble. But anyway, so same thing again. I guess this is showing all the answers already, so I'm gonna. So the process, if you remember, was right. So first I will map this vertical applied force, which is the only force that I know the magnitude of, right? And then so this one is called, we're gonna name these forces by these areas that are on either side of this force, and we're gonna use a clockwise notation system. So this force, I'm going to call it AB, because from the left side it's A, on the right side it's B. And I'm gonna, the way to label that in the force diagram, which is what I'm drawing on the right side, I'm gonna, so I'll take that name AB. The first portion of the name I would use as start point, and then the next point would be called B. So this force, start point is A, end point is B. So now we've actually mapped all of the forces that we know, so that's the only thing we know so far. So then we will place a arbitrary point P, in this case on the left side of the force, and then I'm going to connect with A, connect with B. And what I did here is basically I copied this PA to this zone which corresponds to alphabet A, which is between these two vertical lines, because it's between this force and that force. So this is parallel to that one, and then you extend to hit these two lines, which is the boundary set by these two forces. And the next thing we know is the B, so I'm gonna copy this point line PB to the right side, which is this one. So it gave us these two lines, and this green, it's basically a line to close. So given this given these two lines that I just drew from these, I'm gonna close this into a closed polygon, and then that closing line is what will help us determine what the reaction on either side of the thing is. So once I get the closing line here, I'm gonna copy that back to point P as shown here, and the intersection between this vertical line and that closing line will be called C, and then the important thing is that the reaction on the right side is between B and C, so that's going to be named BC, and so therefore the force that connects point B and point C on this side of the diagram, that's going to be the reaction on the right side. And similarly, the force that's going to connect point C to point A, that's going to be, because this is CA, that's going to be the reaction on the left side. In this case, this point C happens to be right in the middle because this is symmetrical, right? So wherever you put the point P, it's always going to be in the middle point. So if you measure the length of this line, which is 25 inches, because 1 inch represents 10 pounds, so therefore these two reactions are actually 250 pounds each. So that makes sense, right? It's just a refresher, right? So then I would like to ask you to... This shouldn't take a long time, right? Either way, so anyway, so this Google form is not the official homework, and I'm not gonna grade this particular form, but these questions that I have in this file, it's gonna turn into official homework on a separate Google form. So if you solve this now, it's gonna help you save you time later when you're submitting homework. So why don't you I don't know, actually let's do number 1 and have you solve this. So I want to know what the reaction 1 and reaction 2 is, right?
Sorry, for
Yep.
the last part, so we just measure the arrow
Yes.
from BC and CA,
Yes.
and that's it.
And
R1 and R2.
so yeah, so what you do
So
is
we don't need to do the next step, that is like the straight line and adjusting it. We don't need to do that step for now. We don't need
yeah,
to do
this is not necessary. This is
Okay.
so if you so there's another way to draw this diagram, which is to do it like algebraically. So if you read like other textbook, you know, you would see a diagram like this one. So this is only if you want to draw it like this, but for solving the problem, it's really not necessary. But how to get the answer is if you measure the length of BC. In this case, it was it 25 inches? Yeah, it was 25 inches. So because 1 inch equals 10 pounds, so you would do 25 times 10, and that's basically 250 pounds. It's going to be a different answer, so let's do this first. And I don't know actually, so you should be able to type in some number, must be in numbers, so I guess just the numbers, and then you should be actually
So which one are we doing?
section 1, question 1. Sorry, this one actually you have to,
So R1 and R2?
yeah, R1 and R2, yeah, and you kind of have to hit next, submit, but I don't know, this is maybe not the best way, but you know, I want to see how many people are responding. So again, I mean, not much more to explain, but because it's just slightly different, let's do that. So again, you're starting from this, and I'm gonna delete that. So yeah, again, so it just moved slightly. That's the only difference. The labeling system is still the same, A, B, and C. And you're gonna basically start the force diagram by moving this force to the right, or copying that to the right. I'm gonna do, so this one is called AB, so I'm gonna label this A and B. So that's AB. Then again, I'm gonna place this random point on the left side, connect the two lines and match properties just to have the same color, which is not necessary but helpful. So PA, the zone A is here, so I'm just gonna copy this to there. Extend. PB is gonna be here between these two lines, between this force and that force, right? So that's zone B. So I'm gonna copy that line PB to here, extend, and then the closing line is going to determine the point C, which is gonna help us find out what the reaction is. So that's the closing line, and I'm gonna anchor this closing line to point P, and the intersection will be point C. And so what's important to know is like these two reactions are placeholders and they're not shown as correct scale, so I'm just going to delete them so that I can draw in the correct one. So force BC would be the reaction on the right side, and I'm going to zoom in just so that we know. So first reaction on the right side, actually R2 is BC, so I'm going to connect from point B to point C, and the arrowhead is going to be there, right? The next one is CA, so I'm going to start from C and end at A. I'm going to put the arrowhead there, right? So those two are the reactions that we need. So actually this BC is going to be the reaction on the right side. CA is going to be the reaction on the left side. And as you can see, pretty intuitively, but you can see how moving the force, applied force to the left, made the reaction on the left side bigger and on the right side smaller, which makes sense, right? Like there's more weight on the left side, so the column on the left side must be doing more work. And then all you do now is to get the length of this arrow, which is 37.5, and that's still in inches. So I'm gonna, 1 inch is representing 10 pounds, so I'm going to do, right, 37.5 times 10, so that's basically the answer for 375 pound force is here, right? And if I get the length of the other one, it's 12.5. So again, doing the calculation, if you times 10, 125 pound force. And the total would always be 500. Anyway, so that should be fairly simple. So I don't, well, the other ones, I guess I want to demonstrate the other problems, so I'm going to move on. But the other ones is pretty much exactly the same process, but this one's still closer to the middle, so it's going to, so your diagram, so again, these are called moment diagram without explaining too much about it, but you see how the diagram changes as you shift the location of the applied force. And as you can guess, the point C moved from the bottom towards the top as you move the applied load from left to right. So on this, in this case, the number 3, there's a lot of load, so the reaction 6 would be much larger than reaction 5. So that's kind of what's happening. Does that make sense? Another thing to know about this moment diagram is that it's pretty much directly depicting the amount of bending in the beam. So pretty obviously, right? Like, so wherever, so again, I think I explained it last. Is this Monday today or Wednesday? Today is Wednesday. So yeah, I explained it on Monday. Oh yeah, that's right. Anyway, okay, so that actually changes things. I should probably, well, but that lecture actually takes 1 hour, so I'll do part of it probably. But anyway, but I explained last Monday that to calculate the moment, you're gonna, you know, all that matters is the height of the cross section of this diagram, right? So wherever it has the most, so if you take this diagram, right, wherever the highest point, that's where the bending is maximum too. So I think easiest way to imagine, well, one, obviously, if you imagine a beam like this, and if you imagine that the beam was, I don't know, made out of like super flexible material, if it's going to deflect, it's going to deflect like that, almost, kind of, right? Like, well, that's not super correct, but it's gonna, the peak of the bending is at that point of application, right? So in other words, if this beam was to fail or snap off, where it's gonna snap off is most likely right there, because that's where the most bending is happening. So same thing here, you know, that's where the most bending is happening, is right here, right here. Almost too simple in this case, where there's only one applied load. And we did look at these two load conditions Monday, right? So, guys remember, right? Because this is the same thing that was in this demonstration. Well, we can look at it too. Yeah, let's just look at that. All right, so. Yeah, because it takes time to get familiar with this. So let's try again. In this case, we have a one beam, right? Again, same length, and you have 1,000 pounds load at this 1/3 point, and then 500 load at the 2/3 point. This is a section 2 example, right? And then you have these two reactions, which is actually not drawn correctly, but it doesn't matter because they are placeholders. Anyway, so again, you're gonna label these zones between the forces. So quite simply, it's A, B, C, and D. And you start the force diagram. You always want to connect all of the applied forces vertically from tail, tip to tail, right? So the first arrow, which is 1,000, is between A and B, so it's gonna start from A, ends at B. Next one is BC, so it's gonna start from B, ends at C. And then again, this random point P can be placed anywhere where you want to. Right, and then I'm going to connect point P to point A, B, and C. And I have a feeling this is going to be a really deep diagram, so I want to make it shallower, so I'm going to pull it to the side. Anyway, so then I'm going to match the colors so that we can see the correspondence really easily. Then first PA would be at this area A. PB will be in this area B, which is in between these two lines. PC would be at this zone on the right. So that's what we get. Now I need to draw this closing line, which is gonna correspond to this zone D. Therefore, this will help us determine the point D. If I copy this to point P, get the intersections to this vertical line, that part is point D. Right, so now what I'm going to do is, again, I'm going to draw the arrow. The reaction 2 on the right side is between C and D, so it's going to start from point C and ends at point D. And the arrowhead should be placed there, so that's the arrow. Next one is DA, so I'm going to connect from D to A and place the arrowhead there. So then I'm going to copy the arrow CD to the right side of the beam, and I'm going to copy the arrow DA to the left side of the beam. Then in this case, if I get the length, it's 666, so 66. So if I multiply by 10, it's pretty much 667 pound force here, and this one is like 8333, so 833 pound force. Yeah, again, your answer, the reaction, your addition, if you add both reactions, the total number should be equal to total number of applied force. So your reactions needs to total to 1500 pound. So that's how we solved these two load conditions, and we just have these two different conditions. And is it worth having you solve this? It's 10:15. 10:15 is then. So let's spend 5 minutes again for let's do this. It's the top one in the section 2 questions. R1 and R2? Yeah. If it's too slow or too fast, Hello? Alright, so yeah, the time is limited, and I should have stopped the recording. Let's see, still 6. Still working on it, or yeah, you got it? Okay, cool. So yeah, I mean, I guess the process is exactly the same. So I guess I'll skip that. So if you're, I guess I didn't solve it, so I can't really give you the answer yet. But let's just move on, right? Anyway, so there's a couple of sort of particular conditions that we haven't looked at. So I want to cover at least one of them. And also it's spring break next week, so I don't know. When should I make this homework due? After spring break? Okay. So I think what I would do is I'll try to record some videos and stuff, so that you can, look at it to watch it to figure things out. But anyway, so I'm showing a couple of conditions here. So section 3 and section 4, those are what's called this is partially cantilevered, and this is like entirely cantilevered. You've heard the word cantilever before, right? So, but basically, I don't know. This is cantilever. So only supported on one end, it's like sticking out. So you got this kind of partial cantilever condition here, which you would actually get a slightly unexpected result. So let me demonstrate this one, and then maybe I will demonstrate the next one too, because I think it's not really enough time to have you solve 2 of the problems. So anyway, so you have this condition where basically the only difference from before is it's kind of like you move the support to the left and then you move the load to the tip, right? I mean, totally possible scenario. So that's basically what you got here. Like you have one reaction here, another reaction here, and then the downward applied force at the tip. So I mean, without drawing anything, right? Or without solving anything, just think of this condition, right? Like you have, I don't know, 2 poles or something. The beam, the stick is attached to it, and this is like let's say you are hanging on it or something, right? One load is, what's gonna happen here? How does it bend, you think? Anyone wants to like move your finger in the front? Or, oh, some response. Here, come here. So let's say this is like the super flex. I mean, let's imagine like a bamboo stick or something, right? Like super flexible that's attached. I mean, it's fixed on these two ends, and let's just imagine like these are like long poles or something. And then if I jump on this like
a
bamboo
diving
thing,
board, it's gonna go
yeah,
down like that.
right. But it kind of wants to do that, right? Right. It kind of. I mean, even
It's
though
free here from that point, right?
yeah, well, it's fixed, so it's not going to move up, but it really wants to do something like that. So if this is free, it wants to kind of do that, right? So now think about this, right? So these two support points, thanks. In order to prevent that from doing this, what do these need to do is the question. So, are they both pushing up? No, right? One is pulling, right? And so if you could guess that, that's that like. I mean, I think one thing that I remember that Norman. I don't know if you guys knew Norman, but he used to be the dean. But he was saying that the students tend to think like we don't know structures, but like from your life experience with interacting with objects around you, you actually have pretty good intuition embedded in your brain already. So whatever you visualize now is probably correct. So you gotta pull on this end, and you're probably supporting this like this on this side, and on this side you kind of have to like pull it down, make sure that it's so that it doesn't flip over. So that's kind of exactly what's going to happen. So but I'm going to demonstrate it, right? So but anyway, so the intuition says you gotta be pulling on this end so that it's not flipping like this, and you gotta be kind of like supporting that over here. So, but just to confirm that intuition, let's do it analytically, and if you get the same answer, that means our intuition is correct. So again, let's see. So we have. So we have these reactions, which is these are just placeholders, so they are not correct. But there's a reaction here, and applied load here, right? So again, following the same rule, we are labeling these zones between the forces. So in this case, what's on top of the beam, that's between this reaction and this applied load. So this whole entire width is zone A. The next one is it's underneath the beam, between this applied load, that line, and the reaction on the right side, that's zone B. And then the area between here is zone C, right? Then, following the same logic, if I map this applied load on the right side, let's zoom in, that should be called AB. So I'm going to put A on the start point and B on the end point, right? And now, actually we don't know anything else because we don't know what these reactions are yet, so I can't place C. So once you run out of the information that you know, that's when you place the point P on the left side. Let's do it in gray. Then same thing, you're gonna connect P and point P to A and B. I'm gonna match the color so that it's clear. And again, so the thing that's different now is the width of the zone A. Zone A is now the entire width of this beam. So this line PA, I'm gonna have to actually copy this to here, and it has to go the entire width of this thing, because this should correspond to this zone. So that's slightly different from last time. And actually it's going to be a little bit hard to draw the diagram because it takes up a lot of space. But anyway, so then next one is PB, which is zone B. So it's going to occupy this area. So I'm going to copy the PB to here. So now our incomplete force polygon would be like this. So now closing line will be happening between in this zone C. So I'm gonna close this two lines, so to make it into a closed polygon. So that's the closing line. So if you copy this to point P, you will see that it's outside of the force AB. So that's a little bit trickier than before, but that actually doesn't really matter. All you need to do is again just to trim it with this vertical line, which is the extension of this arrow. And so if I take this long vertical line, so that's where basically the point P should, this line should intersect with this vertical line, and wherever it intersects that line is point C. So that's point C on the force diagram. And that again is going to help us determine, let me gray this out so that these are placeholder. So that's going to determine what the reactions are. So if I connect, so again the reaction here between B and C, that's going to be BC. So that's going to be the arrow that connects point B and point C. So I start from point B and I will stop at point C. And that arrow BC is the reaction at that particular point. Then the second reaction is right here. It's between C and A. So that has to be the arrow CA. So I'll connect from C to A and then put the arrowhead on the A side. And that's going to be the reaction on this other end. So, and that's pretty much directly showing the direction of the forces. So this is pushing up at that point, and this is pulling down at this point. And same thing. We can determine the magnitude of the reactions by getting the lengths. Length was 100 inches, so if I type in the length, it's 100 inches. So the reaction here is actually 1,000-pound force upward. So whatever this, if this was like the steel pole or something, that steel pole is in compression here. On the other side, it has to be pulling this beam down so that it doesn't flip over. So it's actually kind of the opposite way, but it's the same magnitude as the applied force. So this is 500 pound, but it's pulling down, and then it's pushing up on the other side. So this is 500 pound downward, and this is 1,000 pound upward. So that's the reactions on these. So again, the section 3 questions are basically changing the spacing of those. So you will have to kind of observe how they change, but the amount is going to change, but in terms of what's happening, it's pretty much the same phenomenon. All right, we got 3 more minutes, so let me also demonstrate this complete cantilever beam, right? So I'll draw these diagrams too. So now you got this, so that was partial cantilever because you have like two supports and it's only cantilever in that portion. But now you got this like entirely cantilevering beam. So it's literally like a stick sticking out of a wall, right? So, and with the, with some weight applied at the tip. So one thing that's I'm kind of ignoring here is one, obviously, there's always total amount of vertical force, right? Like if there's a 500-pound downward force applied, the total reaction should be the same amount, same magnitude and opposite direction. So there's got to be an upward reaction at the wall because that's the only support point. So the magnitudes should be exactly the same. One thing that I'm ignoring here is that if you remember the concept of moment, right? The moment is the force, tendency of the force to rotate the object, right? So, but anyway, if you imagine this stick that's fixed to the wall, and if I hang on this bamboo stick and it's gonna bend, and if I'm too heavy, it's gonna snap off, right? And if it's gonna snap off, it's super easy to guess where it's gonna snap off. It's probably not here, right? Not here, and most likely at the where it's attaching to the wall. That means, so again, that's where all of this moment is happening, right? So in other words, like this force is trying to rotate this whole thing this way from this center point, pretty much. So then the reaction here, obviously you need the vertical reaction here, but also whatever the connection that's happening at the wall, that connection, for example, it can't be a, let's imagine, like, if you imagine like, I don't know, like these two steel thing with a screw in between, and if this thing can freely rotate, this thing basically can't. So if you put this like joint that's completely free to rotate, if you fix the beam, it's just going to do this, right? So then you have to probably tighten this screw so that it doesn't do this. So what that joint is doing is that joint is resisting the moment, right? So that joint has to basically be able to stop this from rotating. So that means one thing that I'm not showing is like the reaction here has the vertical reaction, but also it has, because this one tries to rotate this way, so the reaction here also has this moment on the other direction of the rotation. So anyway, really quick. So then again, to do get the reactions and moment diagram, it's super easy. It's actually, this one's almost too easy, so it's kind of like deceiving, so you might wonder if you're doing it correctly or not. But basically all you do is same exact process. So you would copy this, right? And the only way you can label the top portion is A, so that's zone A. And then you go over this force, so between this force and the reaction at the left side is B. So again, this arrow on the force diagram is AB. That's all the information that I have, right? So then I have to place a point P on the left side somewhere. Then gonna connect point P to A and B. Don't worry, I'm gonna finish pretty soon. So then you get this point line PA and line PB. So first, zone A is here, right? So that's basically where this line gets copied to, right? And then, so where's zone B? Zone B is also here. So this one, actually, it needs to always connect to the previous line. So this line PB should connect to this right here, and then basically gets extended back to here.
Why didn't you connect it to the other side?
because you're always going from the left to right. That's how we are, like, so if you went back to here, if you remember this, like we were always going from, you know, this clockwise system, so A, B, right? So if you follow that order, that's the order, right? So you take the right end point of this line PA and then connect this to there. So anyway, so this is, again, without explaining too much about it, that's what's called the moment diagram, but you kind of already know, actually, because moment is basically, it's basically how intensely things are bending, and this actually precisely speaks to that fact, right? So the maximum moment in this beam, right, there is zero moment at the tip, and the moment gets larger, and it's maximum at the wall, right? So that means it's, again, if you go back to the first visual exercise of, right? So if it's gonna snap off, it's gonna snap off at the bottom, and that's precisely because that's where the bending moment is maximum. And so again, if you think of these beams snapping off, that's called bending failure, right? And the bending failure where it occurs is always where the bending moment is maximum, right? So, right. So that's kind of it for today, and I'll try to cover all of this. I don't know, maybe I'll try to do similar video